We are going to be talking about rotational motion. Remember, there is a difference between rotating and revolving, and both belong to circular motion. We are going to look at today the rotation portion of motion. And when we discuss rotational motion, we do need to make it clear that Newton's first law, which is also known as the law of inertia for linear movement, is also the same for rotating objects. All rotating objects will continue to rotate, or non-rotating objects will continue not to rotate unless they are acted by an outside force, something that will stop it from doing whatever it wants to do originally. Which brings us to rotational inertia, also known as moment of inertia. This is the resistance of an object to change its rotational motion. The higher an object's rotational inertia, the more difficult it will be to change its rotational speed. In order to change the object's rotational speed or state of motion, we need something called torque. Torque must be applied. What is torque? Torque, which is denoted by the symbol tau, which looks like this, is a turning effect which is caused by a force that is acting at a perpendicular distance from a pivot, a hinge, or a fulcrum at some point. This torque produces rotational acceleration or circular motion. Here are some examples. So you see using a doorknob or using the top part of the faucet and turning it, and then also putting leverage on a wrench, so pulling the wrench from side to side, which would create torque. There's an equation for torque, and it is tau equals Fd. Tau stands for torque, and its units of measurement are Newton meters. Force, which is in newtons, and d for distance from the pivot or the axis point, and that is in meters. Leverage is how torque is produced. The longer the handle, the greater the leverage, and the easier it is to accelerate rotation. For example, you'll notice there are 3 wrenches shown below. One is short, one is a little longer, and one is very long. The longer that you have the handle and your hand is on the end, the more force that you can actually give, the more force, the more torque that you would have. One example is when you open a door. It is not the turning of the knob, but it is actually the perpendicular force that you push the door open, because the rotation is occurring here on the hinge. So when you apply a force, with the force being furthest away, so here's your lever arm, the further away that your doorknob is and your push is perpendicular, then you are going to be able to easily open the door and cause the rotation to occur here at the hinge. If you were to have this doorknob closer to the hinge, it would require more force to do the same work that you would need if you just put the doorknob and the push here. So we looked at a hinge and how that works with applying force at a perpendicular angle to some length d from the point of turning. Here we have an example of a fulcrum. When we are placing force in one direction, some distance d from the fulcrum point, we create a turning force which then pulls this lever downward. We have this rotational acceleration from this point called the fulcrum. When the situation looks more like this, with the screw being tightened or loosened, we have this pivoting action occurring. So the axis point is right in the center, and the whole body is twisting around this axis point. And so when you have a force that is pushing in a perpendicular motion to that of the lever here, some distance d from the axis point, we cause the screw to turn or to rotationally accelerate. So here's a question. If you cannot exert enough torque to turn a stubborn bolt, Would more torque be produced if you fastened a length of rope to the wrench handle as shown below? So here is a picture of a girl who has decided to put a rope on the end of this lever. And she's trying to get this to turn because she couldn't get it with just her hands. What do you think? The answer is no. You would not be producing more torque because the lever arm is exactly the same length or the same height. To increase the lever arm, it would be better to use a pipe and put the pipe on the top up here and then pull from up top above the pipe. That would give you more leverage, that would create more torque, and that could possibly give you enough energy in order or enough force to pull that bolt and make it loose. There is a rule, and when the net force of an object is 0, we call this the state of steadiness, and it applies to vector quantities. So it is denoted by sigma F equals 0. The sigma symbol stands for the sum of, and F stands for force. Now here is an example which is mechanical equilibrium. So notice that there are 4 forces, right? There's 30 newtons to the left, 30 newtons to the right, and then 50 newtons up and 50 newtons down. All these are opposite of each other, so therefore the sum of the force is, the net force is 0. Over here, 75 minus 75 is 0, 50 minus 50 is 0. Both of these objects are at rest. They are at equilibrium, even though the forces are different on each object. So just know that the forces can be different and equilibrium can be met in different situations. Now, static equilibrium is an equilibrium for an object at rest. For example, the hockey puck on ice. So when an object is just sitting there, the net force is 0, nothing is moving it, nothing's happening. Now with dynamic equilibrium, it's a little different. Equilibrium for the objects, it's actually moving. The object is moving, but it's moving at a constant speed. So it's moving in a straight line. The net force is again 0. Example is an airplane flying at a constant velocity. So here we have the plane, and it's moving to the left. It's pushing to the left. You have the thrust, and you have the drag pulling you back, which is our net force of 0, whereas you have your up thrust and you have your weight, which is pulling you down. And those also negate each other, so you have a net force of 0. So you're moving at a constant speed. You're still in equilibrium. So now we come to rotational equilibrium. If the sum of all the torques involved that are acting on an object is 0, then what we have is we have a balanced situation. All the torques are balanced. And we can then say that the object will either remain stationary or continue rotating at a steady speed until, of course, an outside force acts upon that system. All right, we've reached the end of our video T-notes. Please make sure you understand this information. Have a great day.